Okay, as harmonic.
Basically, the reciprocal of each term will be in AP.
Yeah, exactly. That's why it's called harmonic. Yes. Yeah. Basically, the most simplest one you can take. You can take any harmonic series. The idea will be same, but we'll just take the simplest one, and that is we will take this itself. So this is just the
Yeah.
harmonic sequence, the most basic harmonic sequence. So the corresponding series would look like 1
1
plus
plus
half,
half. Yeah.
right? So in this one, I'm not really, this is not a contrived example. It's a very clean example, right? All the terms are distinct and
Yeah.
so on, and all the terms are going to 0. So let's first write the observation. So if we call ai equal to 1 by I, then in fact limit ai is 0. So there is no question about this. This we all understand.
Yeah.
Now let us show that this diverges. Okay, so maybe what I will do is let's use better notations. So we will take this till 1 by n, call this hn, okay, and we will show
So limit
that.
AI equals to 0, not infinity.
Yeah, I actually didn't mean to write 0, but yeah, I meant
Okay.
this.
Okay.
Yeah, so show that we will show that limit hn n tend to infinity is infinite. Basically, again,
Okay.
we will just show that it diverges. Okay,
Okay.
and here we will use a very interesting technique. So maybe I'll remove all this. This is all clear. So we will
So
group.
here the rate is not that slow, but it still diverges.
Yes, yeah, and this is like on the borderline of diverging. It
Okay.
diverges
Okay.
very slowly, in fact. And if you just add 100 terms, you might still get the impression that it will converge, because even after adding 100 terms, I think the summation would be not more than 3.
Okay.
Yeah,
Okay.
so it does
Okay.
diverge very slowly, and it's on the borderline of divergence. So we will show later on that if you make slight tweaks to this series, it just becomes convergent. Okay,
Okay.
even the smallest shift on the one side, on the right side, will make it convergent. That's why it's
Okay.
like,
Okay.
that's why I said it's like a central series, centrus at the center, right, on the border.
Okay.
So, but yeah,
Yeah.
let's see why this converges, why this. So we don't need all these limits and all. We understand. We just want to prove that you can make this thing very big. That was just for writing purpose, but we just want to
Okay.
show that we can make this very big. So how do we do that? So the idea is we will group the terms. So what we will do is we will group the term just like I did previously, right? Previously also what I did was just in the previous example, I just grouped the terms and made blocks of 1,
Yeah.
right? I made several blocks of 1 and then concluded that it's divergent. In this case
Yeah.
also we will have to make blocks, but we will have to do that smartly because here the terms are not the same. So
Okay.
the blueprint, the idea is that you will make certain blocks, okay, and each block will be bigger than some number, right? Some number, I don't know which number, okay, some numbers, and these numbers would be clearly going to infinite after adding. Okay,
Okay.
so that's sort of the idea, like a similar idea to the previous one, but it will be in a more complicated way. So let's see how we
Okay.
can make those blocks. It's clear that we want to make blocks and put lower bounds on those blocks, because if those lower bounds are diverging, then this will obviously diverge. So
Okay.
this is maybe a new idea. So let's see. So um, so if you're going to make the blocks, then let's say this is 1 is bigger than equal to 1. So the one block will be alone. Then the half is bigger than, so the half is, let's say, bigger than half. And now I decide to make this block here. Okay. Now in this block, I want to put a lower bound to this block. So certainly I will have to compare it with the smallest term, right? And the smallest term is 1 by 4.
Okay.
So what I'll write it as that this is bigger than 1 by 4 plus 1 by 4, right? It's perfectly
Yeah.
legal,
Sure.
perfectly valid. Now
Yeah.
I should have written a few more terms here. Okay, so till I'll just write it 1 by 8, 1 by 9 till.
So just curious, why are you I mean, taking in twos? You can take in threes, fours, and so on, right?
Yes, but You see, why I'm taking it in twos here, it seems like, though later on I have to take it in fours, because see, eventually I want each of these lower bounds to be same,
Okay.
almost same. Because if they're same, then I can clearly, then I won't have any problem in concluding that they go to infinite after adding. Okay.
Okay. Okay.
But yeah, this is the new idea. So really, it's yeah, I would have not been able to come up with on my own. Yeah. So I have read this, and so of course, then you try to extend the idea and make theorems out of it. That's a good thing. But yeah,
Okay.
but this is really was a new idea when I had seen it in my day. Yeah.
Okay.
So yeah, let's see. So you see again in this block, which is the lowest guy, 1/8. So you'll bound everything
Yeah.
by 1/8, right? So here the good thing is that you're taking 1/8, but you have 4 of them.
Yeah. That's essentially 1/2. Yeah.
1/2, and even here this is just 1/2.
2.
Ah,
Oh,
so
okay.
now you can see the pad. This is now you can understand this is really this is good idea, right? There's something happening.
Yeah. It
So
goes to infinity now. Yeah.
because you can make blocks of half. Okay?
Yeah.
But as you can understand, it's going rather slowly because you'll have to go to like 2 to the power n, right? So you have
Uh-huh.
to go to 2 to the power 4 to make it bigger than half.
But since our series is going, I mean, sequence is going to infinity, no problem.
The series, yeah. So exactly, we have enough terms. Okay.
Yeah.
Like the main point is that if you want to make it bigger than 10, you can do it by taking 2 to the power 10 terms. You might have to take 1,000
Yeah.
terms,
Yeah.
but you can make it. So it's okay. Yeah. But this goes slowly. Okay. And this goes slowly to infinity. That's why it is hard to prove that it goes to infinity. Yeah.
Okay.
Like if something is going slowly towards like slowly to infinity, then it's hard to show that it actually goes. If it's going very fast, then there is no question. Like for example, if we just write
Yeah.
1, 2, 3, we all can say it goes to infinity, right?
Infinity. Yeah.
Yeah. So that's the thing. So if the rate is slow, then the test that you need has to be a harder test. Okay.
Okay.
That's why
Okay.
the root test, ratio test, and all does not work in this case. This has to be done like this. There is another test called the integral test, but that's basically based
Okay.
on this idea only, group and compare. So this is like group and compare, you can
Okay.
call it.
Yeah.
Okay, so yeah, this is a very nice result that it diverges. So
Yeah.
essentially this series diverges. Now let us take certain, so this they had in your notes, and now let's take certain extensions of this result. So maybe we can just, so by the way, we have got a counterexample to this, right? So the terms are
Yeah.
going to
The
0.
converse is not true.
Yeah, I mean, I also gave a counterexample, but this is a much more profound example. Yeah.
Yeah.
So this goes to infinity. Okay. Now let us use it. Let's use the same technique to comment on a different kind of series. Or maybe let me ask a different question, which is like an
Okay.
easier one. Let's say. So now, what can you say about this series? So here I've just put square roots.
You're asking, is it convergent or not?
Yeah, that's the question. Yeah, basically, because all the terms are positive. So
Okay. Yeah. 1 minute. I mean, finally it goes to 0, the final term in infinity. But wait, that
yeah, the terms are going to 0, but yeah.
okay. So I can try the grouping again.
Okay.
Like,
Okay.
uh, like between 1/√2 and 1/√3, the smallest is 1/√3 only.
Yeah. So we can.
Wait, I'm still not sure how many people to pick to group, so I'm slow in that.
Yeah, but okay. When you will realize it. We have to just do trial and error,
Okay.
maybe. Yeah.
Okay. And then, so suppose this is 1/√3 here. Next, suppose I take the next 3 terms.
Next 3 terms. Oh wait. So which one? So your first group is this first 2, or you want to take √3 and √4?
√3 and √4. Just hold on. So 1 minute.
Hmm.
Then the sum will be 2/√4. Oh yeah. Wait. 2/√4, which is 1. Okay, let me try that. If I
Yeah.
take 1/√3 and 1/√4, my essential sum will be 2/√4, which is 1.
Absolutely. Yes, it will be bigger than 1.
And then next, If I take root 5, root 6, root 7, root 8, then my sum will be 4 by root 8. 4 by root 8. That is 2 by root 2. No. That's not. That's root 2.
So it's good, right? Not bad. It's root 2. It's even better.
Okay. It's little bigger than 1. Okay, yeah.
It's all the good for us.
Okay, yeah. And then you can again take 9, 10, 11, 12, 9, wait, 2, and I took 4. Next I need to take 8 terms. 9, 10, 11, 12, 13, 14, 15, 16. It is 1 by root 16.
The next power of 2.
So,
Yeah.
Yeah, so 8 by root 16 it will come.
Yeah, which is even yet
which
better.
is more better, yeah. So I can kind of tell you that it goes to infinity.
Yes, right? It's
So
this is
diverges.
going, and yeah, absolutely. So very good. Means you have just picked the technique, that grouping technique. You have it, right?
Yeah.
But here we will see that there is a easier way to do this from by
Okay.
just but I mean this is like much better in the sense, but as the standard way to do this is that just compare it with this series. Compare it with the series Hn that diverges. Compare the terms.
Okay. 1 and 1 by root 2. 1 by root 2 is smaller than 1 by 2.
Is
It's
it?
big. Is
It's bigger. It's bigger, right?
is bigger. Is bigger.
It's bigger.
Yeah. So every term is like bigger.
Yeah. So there's no chance this has to diverge.
Yeah. If the small one diverges, the bigger one obviously diverges. Yeah.
Yes. And here we are learning another test that's called the comparison test. Okay. So I'll just write it. Basically, that's what you're doing. You're comparing it with a series that diverges, right? And this is bigger, it obviously diverges. So basically, the same idea, you used it once. You don't have to repeat the idea in this second one. Okay. But yeah, so let's just write out the divergent, the comparison, this thing, and let's keep rolling. So nice, picking it up. Yeah. So what
so
is
I
the?
have a doubt. Like if you group it the wrong way, also the answer will come wrong.
No, it will not be wrong, but it will not be useful. Right?
Okay.
If you group
I
it
mean, if you group it wrongly, still it will be visible that it goes to infinity, right?
It depends on how wrong. So there is no one wrong, right? There is no wrong actually, right? If you, there might be other ways to group it which might work, but then there are some ways to group it which will not work.
Okay. Better to go with the best one. Okay. Yeah.
Yeah, it means I'm not saying this is the only grouping, right? You could have grouped it like I like another way is just that you skip the 8, you just take the even powers of 2. Okay, so you group it from this, you group these 4, then you group from this to 16, then you will just get probably 1, 2, 4. Much cleaner. You won't have square roots.
In such a way that it makes sense. Okay, got it.
Yeah, exactly. Yeah, so that you're able to put lower bounds, okay, and that they go to infinity. So there are several ways to group, but not all of them will work. There are some stupid groupings also which will not work. Okay, but yeah. So here we are learning. Here we are just observing, and we'll abstract this out. Another principle of convergence of series, that is the comparison principle. It's more of a principle because really other tests are built around this principle. So
this is our first test.
Which one? I mean, yeah. So yeah, I'll write out the first test. Okay. I mean, basically the first test was this, right? That if limit ai is not 0, then it implies that it diverges.
Okay, got it.
Right? The series diverges. That was baby test. Okay. Or you can write it in.
To make it clear, it either diverges or it's oscillatory.
Or it converges. No. In this case, okay. So in this case, it will not be oscillatory because the terms are all positive. Right? So if limit ai is not 0, then the summation ai.
You take a series, you take a sequence 1, 3, 1, 3, 1, 3.
1, 3, 1, 3.
So this is oscillatory, right?
No,
it goes to infinity. Okay.
The summation. We're talking about the summation. Yeah. The summation. Yeah. So that was our one test. Okay. But very natural tests, right? Nothing really, very deep. And The second test which we can actually write immediately here is that, so I'll write this before the comparison test. 1 by 1 2 to the power p. I'm just using the p letter here because that's how they use it in the books. So 4 to the power p, this thing diverges for p less than 1, less than equal to 1. Can you try to see this? Okay.
Yeah, 1 minute.
Yeah.
If p is equal to 1, it is the HN series, HN sequence series. So obviously it diverges. If p is less than equal to 1, suppose I keep 0, then all will be 1. So each one of them is bigger. Yeah, you're right. It diverges. Yeah.
Right. So this is one of our tests, p test. Okay. This is called the p test. Now again, you see, we are discovering this in such a natural way that we don't have, like, we're not having any problem, right? So like it clearly diverges if this is, and this is also we clearly understand also.
Yeah.
So yeah.
So
Now
if
let
p
us.
is greater than 1.
So I'm just going to do that next. We'll see that. Yeah.
Like I can't say straight away, like if it is not, if it should, it's convergent. I mean.
Yeah, you can't say straight away that it is convergent. No, so you'll have to prove that. But I have made a remark that this HN is on the borderline, and basically that is quantified in that theorem. That if P is bigger than 1, it indeed does converge. Okay, but we will prove it, because I mean that's not a proof. I just said it. Proof meaning that, see, these are not theorem. These are just, have to group and do some trick. So it's fun.
Okay.
Yeah. Let's see. But let's just write the comparison test first, because this is very basic, and we basically use the comparison to conclude this, right? So let's just write it out. So if a1, a2, because let's see, so if a1, a2 dot 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 and these ai's are all positive, right? You don't need positive in this really, but we are doing positive series, so let's just write positive. Okay, now if a1, a2 dot 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 dot, this diverges, okay, and bi is bigger than ai for all I, even beyond a certain point. If that happens, okay, then this obviously, I mean, it doesn't need a proof, right? This summation bi, or basically I can write it as b1, b2, also diverges.
Also diverges. Yeah,
Right?
got you.
This is a very obvious statement. However, there is a limit version of this limit comparison test, which is like a good one, but we will see that. Let's first do the p greater than 1 case. Okay, so yeah, however, just give me 30 seconds to just come from the washroom. Okay, yeah.
Okay, yes, sir.
Yes, so let's look at the p bigger than 1 case. Okay, so let's start with an example. Okay, so maybe we can just write this series as 2. So like we're not going to do for p general p right away. Okay, just to make it concrete. Yeah, because it will be like, since there was a square root here, it was easier for us to first observe, and then you could say later that it just applies for anything less than 1. So it's taking the same approach. Yeah. So yeah, so what do you think about this series?
Okay, 1 minute. I mean, I know that the final term is 0, term I'm telling, and the rate of going there is more faster here compared to the others.
Yes, it is faster. Yeah, compared to the others. But yeah, that's right.
Yeah, I'm just seeing what to group and what just
Yeah,
thinking.
yeah. The grouping technique will work here. Yeah, try it.
Like the others, if I group between 1/3 and 1/4, I mean 1/3 square and 1/4 square, it's 1/4 square. So that sum will effectively come 2/4 square.
Means
2
bigger
by
than.
16, which is 1/8.
So you think bigger than?
I mean, okay, 1 minute. Okay. 1/4. Yeah, obviously bigger than. Yeah, yeah.
Okay, right. Okay.
Yeah, okay, 1/8. No, basically what I was thinking is that previously what happened is we compared everything to HN and we made sure that each term was bigger. And that's why we told when HN diverges, if you take everything bigger, it will also diverge.
That's right.
Now I'm thinking what you're trying to tell is if each term is smaller than HN, it converges. But I'm not getting how that makes sense. Like how can you just say like that?
Yeah, we can't say like that. So that is not correct, because I mean, if you look at it like even here, if you call this square root and something like this, then if you compare it with HN, then each term of HN is lesser than that, lesser than the terms of this series. But of course, HN also diverges. So it may very well happen that this S might also diverge. Okay, it doesn't follow from the same thing, yeah. But yeah, so that's really like really knowing whether it converges or diverges is, I think, is hard. But let's say if I told you that it does converge, and if I ask you to prove it, then maybe you can guide your approach. Yeah, so prove
But I'll
that it.
still group it though.
Yeah, but you have to group it and put upper bounds, because see, when you want to prove that it converges, right? So you have to upper bound it by a series which also converges.
Okay.
Right. You see my point, right? So if I say prove that this, I mean, these can all be explained very well by something called the integral test. Okay, but still, like, let's do it like this. Prove that this converges. So see, if you want to show that it converges, then you want to upper bound it by something which also converges, right? You see, because
you want to upper bound. Okay.
Yeah, like you want to put like you want to make all these things less than something.
Oh, you're telling if I pick a series whose each term is bigger than this, that itself converges, then the small one will definitely converge.
Yeah, something like that. But like not maybe just pick the term, but maybe we have to group and compare. Like you see in the HN also we did, we grouped and we put lower bound, and that lower series was also diverging.
Okay. So
yeah.
So if I pick 1/3 square and 1/4 square, and if I replace each with 1/3 square.
Okay.
No, but why will I? So it will become 2/3 square. Yeah, it's 2/9.
Okay.
2/9. Okay. And then if I pick 5, 6, 7, 8, so it will become 4/25.
So 5, 6.
I mean the next 4 terms, yeah.
Next 4 terms, yeah, it will become 4/25. So 4. I just said 4/5 square. Maybe that's more telling. I don't know.
Okay.
Yeah.
Is this making 1/2 square, 2/3 square, 4/5 square? No, 1 minute now. And it will go on like this, but what does this tell us? 2/3 square. My grouping it
What will be
down.
the next group? You think of that.
After this?
Yeah.
Okay. After this, I should take 2, 4. I should take next 8 terms.
Yeah.
So, 10, 11, 12, 15, 16. Till 16.
Yes.
I mean,
Right.
so 8 by 16 square.
No, 8 by 9 square.
Sorry, 8 by 9 square. Yeah.
Right? 8 by 9 square. Yeah. So basically, this is becoming, now if you can prove that this series converges, then you're done. Right? The way this pattern is going. First of all, you have to understand what first of all, you have to figure out what the pattern is.
Yeah, that's what. Yeah.
Yeah.
2/3 square, 4/5 square, 8/9 square.
What's the pattern between these numbers? That's the question. 3, 5, 9.
I mean, I know each numerator is in GP.
Mm-hmm.
And denominator pattern, okay, 3, 4, 5, 6, 7, 8, 9. I mean, the common difference is in GP.
Common difference is in GP.
The
Okay.
denominators.
That
That doesn't help us.
maybe that helps. Yeah. No. So basically, you're saying that. I mean, yeah, common
5
difference.
minus 3, 9 minus 5.
Yeah. And you see, they are also, each one is like 1 bigger than a power of 2. That's, I think, almost the same as saying that it's a common difference is in GP.
Yeah, that is a thing. Yeah, each one is yeah.
So like the next one will be 15 square, and so on, right? So
Yeah.
the 30. No. What am I saying?
Not 15.
17. 17 square, right? So basically, the general term would be like 2 to the power n, and this would be 2 to the power n plus 1 square.
You're right. You're right.
Now, if you can show that this converges, then you are done.
So the first, okay, 1 minute. Just if I take limit n tends to infinity, it's gonna become, it's gonna tend to 0.
The limit of the term tends to 0, but what does the summation tends to?
No, not that, sir. The first thing that we learn, if at all it is 0, then it converges.
No. If it converges, then it is 0. Right? If this is 0, then you can't say anything. You see, if it is not 0, then you can say that now there is no chance of converging.
Okay, if limit does not equal 0, means it's divergent.
Yeah, but if it's equal to 0, then you can't say anything.
Okay, fine. So I should prove that this converges, okay?
Yeah, summation of this converges.
Yeah, sigma n. So the sigma ka limit should be finite.
Yes. And this looks very much like a GP.
GP.
Means that maybe you could try to compare this with a GP. That's my thing.
Okay. Compare it to GP. Okay, 1 minute. In 1 minute. Just hold on for 1 minute.
Yeah.
2 power n divided by 2 power n plus 1 whole square. Plus 1 minus 1. I split 1 by 2 power n plus 1. And compare it with a GP. How is GP of common ratio what? I'm not getting it, sir.
Okay. So it does. Why I said it looks like a GP is because you can see all the powers of 2's floating around, right?
Yeah.
So let's see. So let's write this in a simpler way. So if you just divide by 2 to the power n, you would get something like this, right? So all I've done, I've just expanded the denominator.
Okay.
Yeah. Right. So 2 to the 2n, 2 to the n plus 1. Now you divide it. Now you see. Try to see, right? See, this is clearly. This is clearly. Oh wait. No. Hold on. Uh, Oh wait. Oh, in the beginning, did you put lower bounds or upper bounds? So no. So there's a slight mistake we have made here. Just a small thing is that this series S is less than this series, right? Yeah. I mean, we have done that
Yes,
basically.
yes.
Yeah. So that's so we are safe. I have written greater than by mistake. Okay.
Okay.
Now you see this is less than. Now this thing, when you divide by things, then this is clearly less than 1 by 2 to the power n.
Yeah, because they're adding more things. Yeah.
Yeah, and 1 by 2 to the power n converges. That summation converges.
Yeah.
So we are done, right? Right. Nice. Good.
Okay. Yeah.
So S was less than this, and then this is less than this. So you saw that there was geometry progression somewhere that the powers of 2 are there. So just trying to write it in the best way, in the simplest way, and then
Okay.
comparing it out. Now,
Okay.
again, this is very good because you've done this yourself, right? This is not I mean, there are faster ways to do this. If you do the exact optimum kind of grouping, then you can get it much faster. But this is like you are like able to do it on your own, right? It's a little longer,
Yeah.
but yeah, it's just nice. Like it's like doing integration and you're making several substitutions and then you're getting the answer. Like, it's not a one shot substitution, but it's your solution. Yeah, but I'll just mention the typical solution or the standard solution also. But this is very nice.
Okay.
So the standard way, I think the way they do it is they yeah, like this. So they group this, and this is less than the powers of 2's basically make it easier. So this is less than 2 times 1 by 2 square, right? And then you go from here to 7, from 4 square to 7 square, and that will be 4 times this, right? Then you go from 8 to 15. Okay, because in the end also you saw we had powers of 2's. Now here I'm just creating the powers of 2's directly. Now, this is not my solution. I see in this. So it's 1 by 8 square into 8. And so on, right? So you can now see the GP because this is half. I mean, it's all less, right? Because that's why I'm taking the smallest term of the group, the biggest term of the group. I'm sorry. So usually 1 by 4, 1 by 8. Now this is like a faster solution, but
Yeah.
it's same thing. Yeah.
Okay.
So nice. So now you see this idea you could have done for anything, right? I mean, even if, but let's just do it. Let's do it for a different.
So just one thing. Here you told prove this converges and we started. Suppose you just give me this series and tell it converges or diverges, then it's hard, right?
Then it's hard. Yeah. Really knowing some, but usually you can compare it with standard series and so on. Okay, this is this is like a central result. This is like any convergence chapter you pick. This will be a theorem in that chapter, not in the exercises. Okay, yeah. So this P test will always be a theorem. Okay. However, there is a test. There is something called the integral test, which you can use to always check whether this converges or not. There is a if and only if condition. Okay, which we will discuss maybe next after this. Let's see. Yes, yeah. So I'm just saying that let's just try to run, just practice this for a different value of P, and basically let's see, after you try it, then we can see.
I mean, we still didn't come to the part where P is greater than 1, right? I mean, like.
So this is one case where P is equal to 2. One special case. Yeah. So I just want you to try one more case, and then maybe we'll be confident enough to say it in general. Maybe let's say take 1.5, rather weird number.
Okay.
For example, now if I take p equal to 3, then you can just say that it also converges because that's going to be lesser.
Yeah.
Yeah, but this is, yeah, let's see how we can do this one.
I should prove that this converges. Okay. Okay, so let me group. Okay. Just thinking which to group. Power 3 by 2, no? I mean, you can group
Yeah.
anyhow, but just looking which makes the most sense. If I pick 1 by 2 power 1.5 and 1 by 3 power 1.5, so it would come 2 times 1 by 2 power 1.5.
Okay, so then this would be less than 2 times 1 by 2. Okay.
Yeah. This one. And the next one would be 4 times, like you take next 4.
Till 7.
It will become 4, 5, 6, 7. Yeah. So 4 times 1 by 4 power 1.5.
Nice, nice.
And 4, and next you take 8, more 8. So 8 times 1 by 8 or 1.5 and so on.
Right.
So this basically yeah, so it's going to become 1 by root 2.
1 by root 2.
1 by root 4. 1 by root 8. Okay. So basically it's 1 by root 2 power n.
1 by root 2 power n. Yeah.
And
so
n is inside the 2, sir.
N is inside the 2. Yeah, right. That doesn't matter in the end. That's the same thing, right? Same number, but yes. That's the way we got it was like this.
Yeah.
Now we have to decide if this converges or not.
Yeah, so if this converges, then ours definitely converges.
Yeah. But if this diverges, then we cannot say anything. Just saying.
If this diverges, or then the smaller one can converge.
Yeah, so then we cannot say anything, but yeah.
This should converge. So this to converge. Okay. It's like another problem now. Okay, wait. I should compare this with some. Okay, wait. Why? This converges. How do I know? Hold on. So any hint?
Yeah, I mean, this is a very well-known series. I mean, you can in fact sum it up. It is so well-known.
Okay.
Yeah.
Okay. Well, yeah, it's okay. Sorry, it's a GP of common ratio 1 by root 2.
Yes. Right. Exactly. So it will converge. Yeah. Yeah. So it's a little bigger, but it will still converge. It's a GPU. That's why I initially ended up writing like this, because I mean that was my instinct. Yeah.
When I see, so from 1 by root 2, 1 by root 2, 1 by root 8, we wrote it in the consolidated form of sigma, right? It's more difficult to make out its GP from the sigma form.
Is it? It depends. It depends on the practice, actually. You know, some people even from here it's easy to make out that it's much easier. Yeah, it's from here it's easier to make out that it's a GP. Yeah, from the sigma maybe sometimes it's hidden, but sometimes the sigma helps, right? And like in the previous question, by writing in the sigma form, we could describe what the nth term looks like this, and that gave me the idea that now I should look at it. Otherwise, I was also not didn't know, because it was like our own way to do, right? Okay, so in fact, This would work for any number that is bigger than 2. Sorry,
Okay.
bigger than 1. I'm sorry. In place of 1.5, even if you put 1.0001, this will still work. Right? You would
Okay.
get a
Okay.
GB with common ratio less than 1. So, and
Yeah.
that would converge. So let's write
Yeah.
out, let's record our results.
Okay.
So this basically, so we have conclusively able to say for all cases of P now, right? So this n power
Yeah.
P, this will diverge if P is less than equal to 1, and it
Yeah.
will converge if P is bigger than 1.
Okay. Yeah.
So we have like done all of it. That the same
Yeah.
core idea was like very same for all.
Okay.
So yeah, so this is called the P test. Okay, and yeah. However, there is this idea that we have used, this grouping idea can be abstracted
Okay.
out. So the group and compare, this idea can be abstracted.
Okay.
So basically in the previous questions, we were grouping by chunks of powers of 2, and we were
Yeah.
lower bounding them by the lowest member of the chunk and upper bounding by the upper member of the chunk, right?
Yeah.
Something like that.
Yeah.
And all along we had this thing that A1 is bigger than A2, bigger than equal to A2 is bigger than equal to A3 is bigger than
So
A4.
whether I lower bound or upper bound, I decide whether the question tells to converge or diverge.
Yes, yeah. If it tells,
Otherwise, we don't know.
otherwise you can try both. You can try comparing it with some series,
Yeah.
you can
Okay.
use your hunch, intuition. Several things are there.
Okay.
Yeah, and we learn
Okay.
more tools, and maybe some of them can help. Yeah.
Okay.
The other thing that our series had is that the terms were decreasing, right?
Yeah.
Yeah. So before we go into this group and abstraction of group and compare, let's just take this series. Let's say if I had a series like this, A1 plus A2 plus A3 dot, 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 okay, such that they're all positive and it is non-decreasing. So it may increase, it may remain
Non-decreasing.
same, it may increase very, very slowly, but it is non-decreasing.
Okay.
Then what can you say about the summation?
What can I say about the summation? I mean, it depends whether it's bounded or not.
Yeah, basically I'm asking that can you
Okay.
say that it's bounded or not?
Oh, can I say if it's bounded or not? It's monotonically increasing. Can I say it's bounded or not? Maybe or may not be.
Think it's an increasing. The sequence itself is increasing. Not the series is always increasing. That we know because the terms are positive. But if the sequence itself is increasing, then you should be
If
able
the
to say something.
sequence itself is increasing and I keep adding more and more, no, it will diverge.
This is again a very straightforward test. It is not even a test. It's very simple, right?
Yeah, it's very simple. Yeah.
So just wanted to get this out of the way because I didn't mention it before.
Okay.
Okay, now let's see.
Okay.
So so we are focusing on the series which decreases. Okay, because in the previous examples also our series were all decreasing and we used the group and compare method there. And if you think about it, the fact that the series was decreasing was critical. Otherwise, you could not group the term and put the lower bound as the last guy, right?
Yeah.
You could not do all this if the series was not in one direction. And we know the other direction case is trivial because that just diverges, so we don't have to worry about that. This one we can think. So the statement is that this. So let's say like this: if A1 plus A2 plus A3, sorry,
And so
A3,
on. Yeah.
so on, converges, then, so here's the thing. So then A1 plus 2A2 plus 4A4 plus 8A8 dot 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 also converges. This is my claim. This is something which we already did, if you think about, right? The groupings that we were doing, but let's prove it. Let's try to do it.
Okay.
But do you feel that we already did some things like this, right? Four
Not
times,
yet.
four, yeah, huh? Yes.
Like I'm trying to link it with
Yeah, okay.
plus 2 plus 4 Yeah, I mean, we've done the process. I mean, making bounds and doing that process.
Yeah,
I'll
so
tell you, basically, what you did is you are taking A2 and A3
mm-hmm.
and you're picking the lower bound there, so it becomes 2A2.
Uh-huh. Exactly, yeah,
Wait,
perfect. That's perfect, yeah. So let me
and
write
then,
it in a
yeah,
separate place. Let me write it in a
yeah.
separate place, yeah. 1 second. So A2 plus A3, very good, no? So this is bigger than 2A2. Okay. No, wait, wait,
Then
wait, wait,
4,
wait. Is it bigger
5,
than
6,
2?
7,
Yeah,
A2.
right. Sorry, yeah, please say again. Can you say again?
Then A4, A5, A6, A7
Ha.
is always greater than equal to 4 times A4.
Mm-hmm.
And the
Perfect.
next will be 8 times 8 and so on.
So on. Right. And yeah, right.
1 minute. A2 plus A3 is equal to 2 A2. No, it's less than equal to, right?
It's less than equal to. That's the problem. Yeah. That's why I was just getting
Yeah.
confused in a minute. Yeah, it's less than equal to, right? Because this is lesser. So we'll have to.
Yeah.
So this grouping will not be good, right? Because if you want to show that this series converges, then you have to upper bound it by something that converges.
Wait, just hold on. So if I want to show that this converges, then I need to find, okay, where each term is bigger.
Yeah, I have to put an upper bound, right?
Yeah.
Yeah.
Okay.
Or
Upper
in
bound.
other
Okay.
sense, you have to put a lower bound on the above series.
I get you. I
Yeah.
get you. Yeah. So we prove that this converges. Yeah, I should put the upper bound on the above series. I get you. Yeah, got it. I'll try that. Hold
No,
on.
a lower bound.
Which on that A1 plus 2 A2.
Oh no, you have to put an upper bound on that. Yes.
Upper bound, yes, yeah.
Yes.
Upper. So wait, just let me see. I should put an upper bound. Okay, so which one should I take? No, I thought I'll do the manipulations on the first one. Now I'm
Mm-hmm.
seeing if I should do the second one.
Okay, maybe that. Yeah, maybe we can do that also.
Like, which should we play with? The given one or the to prove one?
See, if you start with the given one, then you have to put the lower bound. Like you have to group the terms and put lower bounds on them. Okay, and
Okay,
if you
okay.
start with the below one, then you have to put upper bounds on the terms. So that's up to you, the way you want to do it. Both
Okay,
will
okay.
work.
Just hold on. Prove that this converges. Each one which is bigger than this. So if I put upper bounds, okay, let's say I put upper bounds on the to prove one. So then,
Uh-huh.
2A2, A4. So if I put 2A2 and 4A4,
Mm-hmm.
it will essentially become 8A4.
8 less than 8A4? No, but it would become bigger than 8A4. That's no good. We want to
Oh,
put a
it should be
upper.
less than.
Then only we can
Yeah,
make.
so it's less than 4A2.
Okay, yeah, less than 4A2. That makes sense. But then, then the series is becoming even more less in the sense that you will not get this series back. You will not get the upper series. What will you compare it
We
with?
need to use the upper series.
Yeah, you need
Okay.
to bring it in that way. Yeah, you need to bring the upper series somehow.
Okay, okay. Yeah. 100, 100. Hold on, hold on. need to bring the upper series. What to do for it? A1 plus 2, A2 plus 44. So any hint?
Okay, yeah. So maybe as a hint is that you can rewrite this as let's take the 2 common from everything, because I think the 2 is
Okay.
the 2 on the A2 is misleading. That makes us think that we have to make a group of 2 from there, right? Or branch
Okay.
it, but that's not the case. So
Okay.
maybe now you can think. So A1 is not going to create a problem. We can forget about that. From A2 you can.
Okay. Okay. Now I should create. Okay. Okay. Yeah. So A2 plus. Okay. Should I pick? Like if I pick A2 plus 2 A4, that will be A2 plus 2
No, don't
A4.
group this. You have to ungroup them. Because if you want to get the above series, you have to create more terms out of one term. No, not group. You have to ungroup.
Okay.
Right.
So A2. Okay. 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 I mean 2 A4 can be, but then A3 and all is missing.
Yeah, you have to. That's what I'm saying. You have to bring that. You have to split the A4 maybe into 2 pieces. So then bring the A3 in the picture.
Okay. Okay. Okay.
Yeah.
Okay. Okay. I got it. Okay. Hold on. Hold on. I think I'm getting it. Okay. Let's 2 A4. Okay. Okay. I get it. 2 A4 is wait, A3 is less than. I mean, you put an upper arrow.
Or yeah, or like
Less than. Yeah. Yeah. That one. इससे बड़ा है A3 plus A4.
yes. Nice. So this takes care of this. Taken care of whatever. Yeah.
A3 plus A4. And similarly, 4 A8 can be written as A5, A6, A7, A8, and so on. Yeah.
Yes. Now you got it. Yeah. See?
Oh, so this inside series is nothing but the above series which converges.
Exactly. Yeah. The above
So if you
converges.
multiply with a constant number, it will still converge.
Obviously. Yes.
Okay.
Nice. Nice. You see, so we got this. So, but this is not a clean way to write it. That's why usually the theorem is written as I had written initially. This looks much cleaner, right? We're writing it like this. So what we have shown is that this converges. We write actually, the notation is for converging, they just write it like this sometimes. Converges implies that if you just take the 2 to the power ith terms, okay, then it implies that this also converges. Okay, so this, as you can understand now, and looking back at least, that this is like an abstraction of the technique we use there. Okay. So all these tests you see are coming from certain techniques which we do in some concrete case, and then we see, oh, I think we can do this in general. I think we can just need these assumptions and this grouping technique, and that's what we're basically trying to do here, right? And we got this. However, this is much more powerful than this. Even the reverse is also true, and even that we have done. But let's do it again in a abstract way.
So if 2 power I is valid, then even 3, 4, all numbers are valid, right?
No. The two thing is really very, because 2 plus 2 is 4 and 2 into 2 is also 4. Right. Like 2 to the power n plus 2 to the power n is equal to 2 into 2 to the power n. But this doesn't happen for powers of 3s and all.
Okay.
That's a very important, yeah. So it doesn't work for higher powers as far as I understand. But there might be a generalization, I don't know. In that sense, yeah. But now let's prove the other direction. Even that is true, in fact. And we also use that actually in one of the questions.
So which if A1 to A2 plus 4 is convergent, prove the other is convergent.
Yeah. So this is the reverse.
Okay. Okay. If this is given convergent, prove that the other is convergent. Okay. Okay. So basically, if this is convergent, and I want to prove other is convergent, so I should get people smaller than m. They'll also converge. But 2A2 is always greater. 2A2 is always greater than A1 plus A2. No. If I take A2 plus A3, yeah, is always greater than A2 plus A3.
Yeah. Nice.
And similarly, for A4 is greater than A4, A5, A6, A7.
Exactly.
Yeah,
And
so
you see,
basically,
mm-hmm.
the smaller people, yeah, it converges, right?
Yeah. So we are done, right? So it's in the both. Now
Yeah.
we have proved both the directions.
Yeah.
Nice. Very good. So okay. And actually, I mean, the way we did it, we have done it in such a leisurely way, and like we like proved everything ourselves. So it seems not very tasking, right? But this is in
Yeah.
fact a profound. This is actually a good result. It's a powerful result. Okay. So this is known as the Cauchy Condensation Test.
Okay.
So this is Cauchy's Condensation Test. It's an abstraction of the group and compare method. And there are several problems, interesting problems can be made based on this. Okay,
Okay.
condensation test. Why this is useful? Because as we already saw in the previous problem, it was useful. Like if we just apply this theorem in the previous questions, they'll be done in one line,
Yeah.
right? But
Yeah.
because basically this is coming from there. But this is also useful maybe in a series. There are certain series you can think of, where the terms may not be simple, but the 2 to the power ith terms may be simple.
Okay.
You understand? So like series something like this. So if you have a series like 1 by log 2 base n.
Okay.
Yeah, let's just do this as a problem and then we can understand the
So
importance of
hold on. So just one small doubt before you move.
it. Hmm.
See, this one, A1, A2, A3 converges. So A1 plus 2, A2 plus 4, A4 converges.
Hmm.
So you can apply it again on the second step, right? Like A1 plus 4, A2 plus.
Yeah, you can do that. Yeah, you can even do that. Yeah, and sometimes you have to do that in some problems. For
Okay, okay, got it.
4a2, no,
4,
not
A2, yeah.
4a2. Wait, I'm not very confident about that. No. See. So if you apply it again, then it won't become 4a2, because I think then this will become the first term, this will become the second term, this will become the third term, and this will become the fourth term.
Yeah, so basically what we're doing is you multiply 2 to the second term, 4 to the third term.
No. You multiply 2 to the second term, right? Yeah, that's right. So it will become 2b2, and then 4, but then this will not be there, right? It will become 32a8, right?
Okay, you have to skip a few terms.
You,
Okay.
you have to just take the powers of 2's, right? But now you're taking
Okay.
powers of 2's.
Okay.
You see, yeah. So you will have to skip a lot of terms then, yeah. So
By
after
retaining the first term.
a first term will be retained because 2 to the power 0 is 2 to the power 0, right? I
Okay,
mean,
okay, got it.
in that sense, that will always not change. But yeah, it will. The later terms will change. Okay, so you have to only
Okay.
take. You will only be left with those terms which have powers of 2. So you'll be left with like a1, a2, um, uh, a6, 2 to the 2 to the power 4, then 2 to the power 8, 2 to the power
Okay. Yeah.
16. Those powers of 2 which are also powers of 2, right? Yeah,
Okay.
probably in some very hard question that will be needed. Usually
Okay,
not.
sir.
Yeah. So, but yeah, that's interesting. That's like an iteration. Yeah. But okay, let's try to do this question. We can understand the importance of this one. So let's try to
Okay.
do this one.
So what should I do? I should prove it's something.
Yeah. You decide.
Wait, I should tell it's convergent or not.
Yeah. And then prove it also.
Okay, okay. 1 by log n base 2. Okay. So if I write it down a little bit, it's basically 1 by. Wait, n won't start from 1, right? Obviously.
Oh yeah, in this case, make some adjustment and start from 2 maybe.
Okay. Yeah. Yeah. So this is a yeah. This is a each term is increasing each term. Like A1, no, each term is decrease. I mean, here it's A1 less than A2 less than A3.
No, the terms are decreasing, right? Because
So like you start with log 2, log 3, log 4. Now
but this is
log
1.
4 is obviously bigger, right?
No, but this is 1 by that, right?
Oh, sorry, I didn't write that down. Okay. Yeah,
Yeah.
sorry. It obeys the above thing.
Yes.
I mean, to prove this converges or wait, hold on. Do I have to group them? So should I try to use the above result or something?
First, you can just think logically. You can try to compare it. You can also try to use the above result. Yeah.
Okay.
Or you just apply the above result and see what you get. Because that's would be the fastest, maybe, if that
To
works.
apply the above result, one thing should be given, right? If one is convergent, then only I can apply it on that, right?
No, but let's just apply it and see whether the resulting series is convergent or not.
Okay.
Yeah, that's
Okay.
the experiment you have to do. Yeah.
Okay. So if I apply it, I'm going to get 1 by log 2, and then 2 times A2, which is 2 by log 2, 3, and 4 times A4, 4 by log 2 base 5. Okay. Yeah, so if I apply it, I'm getting sigma n by log n plus 1 base 2.
N by log n plus 1.
N plus 1 base 2.
No.
After applying.
No. How are you getting this? You have to skip the terms. Are you skipping the terms? No. This you will not get. You have to skip the terms. You will get a power of 2, right? So
if I apply that, I will get, see, the given series is 1 by log 2, 1 by log 3, 1 by log 4, 1 by log 5.
yeah.
If I apply that, I'm going to get 1 by log 2, 2 by log 3,
1 by log 2, yeah, 2 by log 3,
2 by log 3, 4 by log 5,
4 by log 5,
and then
8 by log 9.
yeah. So you will get sigma 2 power n minus 1
And n minus 1, 2 power n minus 1, yeah,
divided by log n.
No, it's not.
No, wait. Log, wait, hold on. Log of 2 power n minus 1 plus 1.
Exactly,
I
yeah.
mean plus 1 normally.
Yeah, right. Yeah, but it's the denominator is roughly n minus 1. More or less.
Okay.
Right, because see, this 1 is not going to make much difference, right, in the end, especially when n becomes big. So this is roughly 2 power n minus 1, and that is roughly just n minus 1. And that is equal to n minus 1.
Yeah, you're right. Yeah.
So what it essentially comes out to be is 2 to the power n minus 1 by n minus 1. Now the question is, so if this is convergent, if and only if this is, so this is convergent. I mean, they are basically, you have to check the convergence of
it
this.
goes 2 ways, yeah.
Yeah, exactly. And but this is clearly divergent.
Wait, so 1 minute. The above theorem, if you prove one converges, the other converges, and the other converges, this one converges.
Yeah.
Same applies for diverges.
Now, that is a logical consequence. Yes, it does apply, but it doesn't even need to be said. I'm saying that in the sense that just follows logically. Because see, if this converges, it implies this converges, right?
Okay.
So it means that if this diverges,
that has to diverge.
That has to diverge, right? Because if that was converging, then this would also converge, but we assume that it diverges. So yeah.
Yeah.
So it's
So
like,
now 2
if
power
A is
n minus
equivalent to
1 by.
B, then negation of A is equivalent to negation of B. Yeah, go on.
Yeah. So this 2 power n minus 1, I should talk about this series now.
Yeah, now we can only focus on that series, exactly.
Then 2 square by 2, 2 cube by 3, 2 power 4 by 4. Okay. What do this is? 2 square by 2, 2 cube by 3, 2 power 4 by 4, 2 power 5 by 5. In this series, what can I comment about 2? If I take 2 common, it's going to be 1 and then 2 by 2, which is 1, 4 by 3, 8 by 4, 16 by 5. So
Exponential, right? More or less.
yeah, matlab the numerator is very exponential.
Yeah, and you can just check that. You can just do the most. So when you see that, then it should diverge, right? And you can just check it by taking the limit of this when n goes to infinity. That's not 0.
Okay.
Like
Okay.
even the term is not going to 0, right? Even this is not even this is going to infinity, right?
Okay. That means it converges.
No,
It diverges. I mean,
diverges. Yeah, I mean even the terms are going to infinity. Think about that.
infinity. Yeah.
So the
Yeah. Yeah.
series would obviously go to series is like the summation of all the terms. It will go to double infinity
Yeah.
if there is any such thing.
Yeah.
Something like that, right?
Yeah.
So you see, this problem becomes very obvious, right? If you use this result, if you use this
Yeah.
condensation, basically you're condensing the series, right? That's the
Yeah.
application. However, I thought you would do it in a better way. This was much faster
Okay.
because you see,
Okay.
try to compare it with HN. So compare it. So compare it with HN. HN meaning the harmonic
Just a
series.
doubt. Here
Mhm.
is n is equal to 2. I should compare with hn also where n is equal to 2.
Yes, term by term comparison. I mean, you can
Okay.
decide that, but in this case, term by term comparison is the best thing. But you don't have to
Okay.
always do
Okay.
that. You can shift a term here and there also.
Okay. You have to compare. Hn is what 1 by n power p, right?
No,
1 by
HN
n. Yeah. 1
HN
by
is just
n.
1 by n. Yeah, just 1 by n.
Yeah. So, and this is 1 by log 2 base n. So just hold on. So 1 by 2, 1 by 3, 1 by 4, 1 by 5. And here it is 1 by log 2, 1 by log 3. Yeah, so if I take log, the value decreases.
Yeah, right. Because log is the power that you need to raise the number that you need to raise to get n.
Yeah, so
Right.
the
That's
overall term increases.
absolutely, yeah. And so it's obviously
So,
diverging.
yeah, it's obviously diverging. Yeah,
Yeah. So
yeah.
this was like this was an obvious thing, right? But
Okay, okay,
but yeah, just maybe that's what I'm saying, that you missed it. So
okay,
then you
okay.
might say that then I don't see why this theorem is so useful that we proved, right? Because this was obvious
Yeah,
anyways. But let's do an
yeah.
example where it is not obvious.
Okay.
So whether it converges or not. So there was one log, it could not save the series. It still diverged, right?
Yeah.
Obviously. So however, if I put n log n, then how would
Mhm.
you do it?
Okay.
Okay,
First, I'm
by
just
the way,
comparing.
just one thing, yeah, before I see this, because there was a slight thing which you could have done better in the previous things. So this one, you see, when you are taking when you're applying this condensation test, you're taking the terms which are only powers of twos, right?
Okay.
So
Yeah.
you can take a bit of liberty in this series, and you can write this series as starting from 0, okay, and the second term being this, and the third term being this, so that it's just arranged in order. So it's just basically I'm just shifting the series a little bit, okay, just to make the terms you know uh, just translating it, okay? So the terms are written better. What this does is, now if you apply the condensation, it's much faster, okay? Because now if you take 2A2, then you get 2, right? If you take 4A4, right, then you get 4 by 2.
Mm.
You see, because this is the fourth term, right?
Yeah,
So if
yeah,
you take 4
yeah.
by this is just 2. So now every term which is a power of 2 is a very good term.
We will always add 0, doesn't do anything.
Yeah, it doesn't do anything, but it changes the thing here, right? Because next time when you take this log a base 8, then this is very simple, right? This is just 3. So yeah,
Yeah,
so it's, so we don't have, you won't get all this thing, you know, like we got here a bit ugly expression. So yeah, sometimes you
yeah,
should just, you just shift and all that, and yeah.
yeah.
So with that in mind, we can try this problem.
Okay. 1 by n log n. Okay. This is basically, if I write it out, it's basically 1 by, it starts from n is equal to 2, of course, yeah.
Yeah.
2 log 2 and 1 by 3 log 3, 1 by 4 log 4, okay. And now, okay. The question is 1 by 2 bigger or 1 by 2 log 2 is bigger? Just hold on, sir. Hold on. Let me take the coefficients to the power of the log. Basically, you've given sigma 1 by log n power n.
Okay, nice. You can see it like that. Yeah, that's obviously the same thing. Yeah.
1 by log 4, 1 by log 9.
No, it will not be 1 by
Is
log
1 by
9.
2 bigger?
It will not be 1 by log 9. It will be 1 by log 27.
Sorry, 1 by log 27. Sorry. Yeah. Cube. So the question is 1 by 3 bigger or 1 by log 27 bigger? Wait. No. Or let's check the other way. Is 1 by 3 bigger? 1 minute. Yeah. So is log 3 greater than 1?
Log 3. Think about it. See, so log 3 base 2. This is basically the power that you need to raise 2 to get 3.
Huh. Oh, so basically 3 is 3 greater than 2? Yeah.
Yeah, because you have to raise it to a power which is more than 1, right? To get number bigger than 1.
True. So basically, I know that, yeah, so each term is, each term is bigger. So it definitely diverges.
Bigger than what?
Is bigger than the HN.
No, it is lesser than the HN because there is a 3 here and there is a 4 here.
How is it lesser? Like, suppose you pick 1 by 4 and 1 by 4 log 4.
Yeah, so 1 by 4 is obviously lesser, right? No, I mean it's bigger, right?
1.
Hey, you're multiplying by log 4.
1 minute, sir. Yeah, so log 4 is greater than 1. Just hold on, sir. 1 by 4 is greater. I'm sorry, yeah.
Yeah.
So each term is smaller.
So that's no use for us. That's why this is a good
That's
problem.
no use for us, yeah.
So this so it means that this series we cannot compare with the harmonic series, unfortunately.
Yeah.
Okay. So we'll have to do something different.
So let's try the condensation.
Let's try the condensation.
So if I condense, I'm going to get 1 by 2 log 2, then 2 by 3 log 3. No, wait. Just hold on. Wait. Let me add 0, okay? So if I add 0, the zero still stays, right? The first term.
Yeah, yeah. Even if you don't add, you'll not get a wrong answer. Just your calculation will be
Okay,
a little
okay.
messy. Yeah.
Okay, so 0, then 2 by 2 log 2, and
2
4 by
by
4 log 4.
plus 4 by 4 log. No. Okay. Yeah. Right. Right.
Yeah. And then 8 by 8 log 8.
Mm-hmm.
And so on.
And so on. Right. Hey, very good. Yeah.
So basically, we are getting 1 by log 2, 1 by log 4, 1 by log 8,
Yes.
which is nothing but 1 by log 2, 1 by 2 log 2, 1 by 3 log 2.
But log 2
So
base
it's
2 is just
basically
1.
a,
Yes.
sir?
Yeah. Right. Yeah. You said GP, right? I was going to say the same thing.
Yeah, it's a
It's a
GP.
GP. Yeah. 2 cube and whatever. Wait. No. It's not a
No, no,
GP.
it's
Wait.
not
What
a
am I?
GP, sir.
Sorry. Yeah.
It's coming 1 by log 2, 1 by 2 log 2, 1 by 3 log 2, 1 by 4 log 2.
Yeah. So it basically becomes a harmonic series.
Harmonic series.
Right. Because you
Yeah,
see,
yeah, yeah, correct. Because the reciprocal is in AP.
exactly. You see, with a naive comparison, we were not able to compare it with the harmonic series. A term by term comparison with the harmonic was not working. But a
Yeah.
grouping and comparing, basically condensation theorem is this is basically grouping and comparing. A grouping and comparing with the harmonic series is working.
Yeah.
And we know that the harmonic series diverges, and so this also diverges. So this diverges.
Okay.
This also diverges. So this is another
Okay.
beast in the room
So
because
any harmonic series diverges.
yeah, this we know, right? This diverges 1 by 2, 1 by 3, 1 by 4. This we just proved diverges.
Yeah, yeah. But this is 1 by 2 log. Okay, okay.
No. It's not
Yeah,
1
got
by.
it. So you can take 1 by log 2 common. Got it, got
Yeah,
it.
yeah. Log 2 is just 1, right? Because log 2 base 2 is. Oh, no. It was base 2 to start with. Yeah. But you're right. I mean, in fact, in the end of the day, it doesn't even matter, right? The base doesn't even matter. You can take any
Yeah,
base actually. Yeah.
you can take it common in
You
the
can take
end.
it common. You can put it like that, or you can also just say that log n base e. You can write it as log n base 2 by log e base 2.
Yeah, yeah. Got it,
This is
sir.
some
Yeah.
identity, yeah, base
Yeah.
change. So in
Yeah.
any case, you understand that. So, but the thing is that look, this is a series which is even slower than the harmonic series
Okay.
because we understood the terms were lesser, right? When we just do term by term comparison, right? The terms were lesser
Yeah.
than the harmonic series, right? 1 by n log n is less than 1 by n, right? So this is even slower than the harmonic series, but it's still, I mean, it's slower than the harmonic series, but it still diverges. Okay.
Okay. Okay.
Yeah, and that we found out by so putting one log did not help. Now,
Yeah.
actually, in fact, even if you're going to put log of log n, if you're going to take a log of this again, then you
Okay.
can apply the condensation twice. We will not do that because I don't think they will ask such questions in the exam. But you can
Okay.
do it in any ways, even if they ask, just apply the Cauchy condensation 2 times, or just apply it once and use the fact that this diverges.
Uh-huh.
This will
Yeah.
also diverge, even though this will be even more slower.
Okay. Okay.
Wait, am I correct? This will be more slower. Wait, 1 second now. So if you're going to take a log, if you're going to take a log of log, it's going to become lesser. No. Sorry, this will actually be faster, right? This will be faster. I mean, this will be this term by term will
But it
be
gets
bigger than.
smaller quickly.
Yeah, so the denominator will get faster. Then the number will get faster. This is actually bigger than
Faster,
this.
faster. Yeah.
So this is
Yeah.
not. So this is what I'm saying is bullshit. This is wrong. Um, so we'll just have to tweak this like this. So if there are two like log n times log n, even this will diverge. Though this is slower, right? This is slower, right? This is less than 1 by n log n. So you can't
Yeah.
use that to conclude, but you can apply the Cauchy condensation on this also, and you can show that it indeed diverges. Okay. So no matter
Okay.
how many
Okay.
logs you place here, you will not be able to save the series. You can make it slower and slower, but it will still diverge.
Uh-huh. Uh-huh.
Okay, yeah. So these logs of wood are not going to save. So it will still sink to infinity,
Yeah. Yeah.
something like that.
Yeah.
So, uh, Yeah, that is the thing about this condensation thing. And now there are other
Okay.
questions of this that can be asked, but for